to this wonderful event. So I did PhD at TIFA, and although I was not a PhD student of Spenta, he gave me, I did interact with him, and he gave me advice when I joined. Among some of the advice was to read Poliakov's gauge field in strings instead of Weinberg. And of course, if any student comes to him and tells him he's interested in string theory, the first paper, at least one of the first papers they're told to read is usually a review by Kogut on lattice gauge theories and spin systems, which is nice. So I did both those things. And of course, I joined in 2007, so I benefited a lot from ICTS activities. I think right after I joined, we had the monsoon workshop and numerous schools, such as the Asian Winter School where Strominger spoke, and there's a random matrix school where Marino spoke, which I attended, so that was very nice. So I thank him for all he's done for science and setting up ICTS, which I hope I'll continue to benefit from. Okay, so in this talk, I will talk about work related to the one paper I co-authored with him, which was Chern-Simons theory coupled with vector fermion matter. This work initiated this study of the large n limit of Chern-Simons theories coupled to vector matter, and it's led to a lot of follow-ups, but although fairly recent, of course, it crucially relies on classic techniques for solving large n quantum field theories that Spenta and others helped develop during the earlier parts of his career. So first, I'll just review part of this paper, then I'll describe some more recent work with Simone Giombi, my student Chern, and some other students, Vladimir Kirlin and Zhenya Schwarzkopf, where we calculate the 1 over n, the anomalous dimensions of the single trace operators, of all the higher spin single trace operators to 1 over n. And then at the end, if there's time, I'll just describe some preliminary calculations to generalize the above work to bifundamental Chern-Simons theories, which is another area that I think Spenta is very interested in. And last time I met him, he told me to keep focusing on that area. So, okay, so as you know, Chern-Simons theories with matter are a simple example of non-supersymmetric CFTs that are a line of fixed points. Okay, because the Chern-Simons coupling is K, is discrete, it cannot run, and then n over K, although it's effectively continuous, it also cannot run. So you have already a line of a coupling constant that you can change, and any other couplings in the theory you would presume can be tuned to fixed points, or in the case of fermions, there's no other coupling. So it gives you an easy way of constructing non-supersymmetric conformal field theories that can be taken from weak to strong coupling, and then therefore provide examples of non-supersymmetric strong weak dualities. And of course, there are at least two different large n limits, large n vector models and large n matrix models. Okay, although there's a gauge theory in Chern-Simons, it's still a large n vector model, just like the 't Hooft model, because the gauge field is non-dynamical. Okay, so therefore, we expect that if you consider UN Chern-Simons theories coupled to fundamental fermions, it would be exactly solvable. Okay, so to solve it exactly, the straightforward way to see that it's exactly solvable is to follow Spenta's paper here from 1981, where you can drive a Schwinger-Dyson equation for the exact fermion propagator in light cone gauge. So I'll just review that calculation. So we write the action for Chern-Simons theory coupled to fundamental fermions. If we go to light cone gauge, the cubic vertex vanishes, and the action looks like this. You integrate out the gauge field to get an effective quartic interaction for the fermions. And then there's the standard trick which in matrix models and other things where we take the full complete derivative this total derivative, and that gives us this self-consistent equation for the 2-point functions, the 4-point functions, but in the large n limit, the 4-point function factorizes to yield a integral equation for the exact propagator, which we then solve, and it gives a fairly simple result. And once this is exactly solvable, then of course everything else is also exactly solvable. So you can either try to redo the above calculation at finite temperature to obtain the thermal free energy of the theory, or you can calculate gauge invariant 3-point functions or 4-point functions using similar techniques. So that's the essence of Chern-Simons vector models. I'll just briefly mention the main follow-up that Spenta and has worked on others, which was you can also consider the same instead of Chern-Simons coupled to fundamental fermions. We can consider Chern-Simons coupled to fundamental bosons, or Chern-Simons coupled to critical bosons, or a sort of a Gross-Nivel model of critical fermions, and all the 4 theories are exactly solvable in the same way. And you find immediately a duality which is completely analogous to level rank duality, where at weak coupling, a theory of bosons can be equivalently described as a strongly coupled theory of critical fermions and vice versa. So that is the very nice consequence, and there's still a lot of work extending this to finite n. Okay. Another duality that these are related to is that the Chern-Simons theories are dual to higher spin gauge theories. Okay, then that's because there's only a small spectrum of single trace primary operators, and the anomalous dimensions of these vanish at leading order in 1 over n. Hence, the dual, if it exists, would contain one massless high spin gauge field for each spin. Okay. Okay, and the anomalous dimensions of the currents are related to the divergence. So here I'll review the work with Giombi, where we calculate the 1 over n anomalous dimensions. Okay, so the single trace operators in the theory are easy to enumerate. There's one single trace primary for each spin, and they all have scaling dimension s plus 1, except for the scalar whose scaling dimension is 2. By demanding that the currents are traceless and conserved, we can find the explicit form and package them into a generating function. In the interacting theory, the only difference between this generating function and the other is that classical derivatives are replaced by covariant derivatives. Okay, so these are the only single trace primary operators in the theory. We can ask, okay, the s equals 1 and s equals 2 currents are, of course, conserved in the interacting theory, but all the other higher spin currents are no longer conserved. So we can ask, what's the most general allowed form for their divergence? So if you just want to match scaling dimensions and spins, you'll see that the only terms that can appear on the right-hand side of this divergence equation are either double trace operators or triple trace operators. Okay, where S1 and S2 have to be less than, when you add them up, have to be less than S. Okay. Okay, and we can not only say that they're double trace operators, but we'll be able to completely determine the lambda and n dependence of these functions, and also the particular combination of derivatives acting on these, just using conformal invariance. Okay, so let's focus on the double trace term. So we can fix the n tilde dependence of this coefficient that appears in front by taking the 2-point function of both sides of the equation with JS1, JS2. Okay, this relates that coefficient to a ratio of 3-point functions and 2-point functions. You can find the planar 2-point and 3-point functions by direct Feynman computation, or more cleverly using Alzheimer's techniques. And that allows you to find these coefficients, which have a very nice form that in terms of a variable called lambda tilde, is lambda plus 1 over lambda inverse. Okay? And it tells you also that there's this coefficient is proportional to 1 over n, which implies the anomalous dimensions are also 1 over n. So at leading order, all the currents have vanishing anomalous dimensions. We can also constrain the particular combination of descendants represented by JS1, JS2 by requiring that the divergence is a primary. That's because since initially this was conserved at n equals infinity, then the 1 over n corrections, then it's initially a short representation, so it has to be combined to a long representation by combining with another primary operator. And that's fairly straightforward using the conformal algebra. Okay, so essentially we can determine the divergence uniquely up to one overall constant that just depends on the spins. This constant could be determined from first principles using slightly higher spins broken symmetry, but we simply fix them using the classical equations of motion to be like this. So inserting this into the formula relating divergence and anomalous dimension, we finally get expression for the twists of the highest spin currents, and we see that there are two different lambda dependencies. One comes from double trace operators involving a scalar, and the other comes from double trace operators where all the spins are non-zero, and they have slightly different terms. And by summing up the contributions from each one, we can explicitly determine the 1 over n anomalous dimensions for all the spins. Except for spin equals 0, which this doesn't work for. Okay. Okay, the contribution from the scalars is fairly simple. The contribution from the higher spin from the these is more complicated and contains this harmonic sum. So the harmonic sum in the large S limit gives you a log S, okay, which and takes a fairly simple form. That log S behavior disappears at weak and strong coupling where there's no gauge field, and you're just in the theory of critical bosons or free bosons, etc. Okay, so which is, and of course, but we have the explicit expression for any finite S, and it agrees with various checks such as expansion and conformal spins. We can interpret this coefficient of log S as sort of the cusp anomalous dimension at 1 over n of the theory, and it would be nice to reproduce it by Wilson loop calculation. And we expect physically this corresponds to, these are masses of higher spin gauge fields which acquire a mass due to loop effects in a holographic description. So in principle, we could try to reproduce these from Vasiliev theory.
And since your calculation only uses 3-point functions, it's automatically the same on the others.
Right, it's automatically the same, but it also turns out these are the same both for the quasi-boson family and the quasi-fermion family, which did not have to be true for the duality. Okay, and so it, and of course, though these spin-dependent numbers we got from, so we didn't use the full 3-point function, we didn't use this normalization. So to do that, we had to take divergences from classical equations of motion. So in some sense, that's another check, because, okay, and these C's are like structure constants, so from there we can get more, which are closely related to the parity odd forms for the 3-point function. So once we know the divergence, we can also write down explicitly the parity odd 3-point functions outside the triangle inequality.
Do you have an analytic form for that?
We have a closed form in a particular kinematic limit, but on a case-by-case basis, you can write it for any limit, sort of, yeah. Okay, so in last 10 minutes, we'll just generalize this even further. So another consequence of this work was that we can find that Vasiliev theory apparently it has to arise as some phase of string theory, because, okay, I mean, essentially, this essential feature of the duality is that any vector model is probably dual to a higher spin gauge theory in the large n limit, and that means ABJ theory with m much less than n. Recall ABJM is un cross un, but you can generalize it to um cross un, and it still has n equals 6 supersymmetry, and has an interpretation within string theory as type 2a string theory with some fluxes on CP3. So ABJ theory with m much less than n is effectively a vector model, and the arguments above sort of indirectly essentially apply. So we know that it should be dual to a Vasiliev theory, and these guys constructed it. So there's an n equals 6 supersymmetric Vasiliev theory that they constructed, which also has Chern-Eton factors on each of the higher spin gauge fields. And as you increase m over n, we go to ABJM theory. Here, m over n is like a gravitational 't Hooft coupling. So somehow these higher spin gauge fields combine to turn into Einstein gravity as you increase m over n, or the gravitational 't Hooft coupling. Okay, so this is a very nice picture that these guys emerged. And a question that I think Spenta is interested in, and myself, is of course, this is the picture which is sort of within string theory and has n equals 6 supersymmetry, but we can draw the same picture without supersymmetry. So nothing stops me from writing a un cross un Chern-Simons theory coupled to bifundamental fermions. It's automatically conformal because there's nothing else you can write down. Okay, when m is less than n, we expect it to be dual to a Vasiliev theory perhaps with Chern-Patten factors. Okay, and then we can increase m over n in the field theory side just to get a bifundamental Chern-Simons theory. In the dual picture, that would presumably also correspond to increasing a gravitational 't Hooft coupling. So the question is what happens here, analogous to type 2a supergravity. And the natural conjecture is it could be a relatively simple non-supersymmetric theory of gravity, which is why it's interesting, although it's very difficult to study. So just some words about that. So some of you have seen this before. Okay, this theory is clearly conformal, and like ABJM emits a large n limit. Okay, so what can we say about the holographic dual of the theory? Okay, so small changes in the 't Hooft couplings, which are effectively continuous, would correspond to 2 dilaton and axion fields in the bulk. In addition, the conserved stress tensor and U1 current in the UN cross UN theory would correspond to a Maxwell graviton field in the bulk, but there appear to be no other protected operators in theory. So if all the anomalous dimensions diverge, the dual could be as simple as Einstein-Maxwell axion dilaton gravity with a small negative cosmological constant. There's another large n limit that might exist, just to speculate, which okay, you see, and when at fixed k, when k is 1, and AB.
In your previous there are no protected operators, but there's no parametric gap either.
Well, at strong coupling in ABJM, there's a parametric gap.
Right.
And that's supersymmetric. So just looking at this picture, we might guess by analogy a parametric gap should emerge.
He's hoping there is.
I mean,
supersymmetric theories, it's very difficult normally to find parametric.
But you will solve the cosmological construct.
Yeah.
Right. So if you could solve this at
If you can solve
the cosmological construct
at k equals 1. If you can do it at finite k, then you solve it.
But
right.
I mean, it's not. I mean, by analogy, of course, one might hope, but it's not very easy in the non-supersymmetric quantum.
Well, even in the supersymmetric one, aside from localization, we wouldn't have any argument that it diverges.
But supersymmetry stabilizes.
Yeah, I mean, usually it's not even easy to get a line of exposure.
No, I agree.
So already that's there. So
yeah, one has to stick to that.
Right. So I mean, that's. That's yeah.
It's an interesting question.
It's possible that the theory gets unstable somewhere around.
Exactly.
Right. So there's various things that can go wrong.
But if it goes all the way,
Yeah.
it's good.
But if I have to guess, I would say it would get unstable. Right? It'll follow
Right, it's possible that it gets unstable. And of course, if you were to study it, if you could define M theory limit at fixed K and large N, then there would be no lambda, and hence the theory would have just, say, Einstein-Maxwell gravity with a small negative constant. Because then you don't have a Dilton or axiom. Right. And just for kicks, you could replace it with ON cross ON coupled to real Majorana fermions.
Get rid of the Maxwell.
And then if there's a finite K large N limit, that could be just pure Einstein gravity with small cosmological constant, because there's no U on the field. Okay, so it's, and you could add flavor symmetries to add gauge fields as you wish. So you can imagine a bunch of theories, but we really can't say much about them in a calculational way. But is there is there any way we could do any calculations at all in these theories? Because they're effectively they're large N matrix models, so there's a web of diagrams, so you can't sum them up. So studying the series at strong coupling appears impossible, making tests of conjectured holographic duals difficult. But again, since UN cross UM theory is exactly solved when M is much less than n, we can instead just to try studying the theories when in perturbation theory in M over n, because when M over n is 0, it's exactly solvable, and then each order in M over n is essentially a vector model calculation, just more and more complicated. Okay, so just like the 1 over n calculation, so perturbation theory in M over n takes us from an exactly solvable large N vector model to the unsolvable large N matrix model. So I tried some calculations. I set up some calculations in this theory. So UN cross UM Chern-Simons coupled to fundamental fermions. There's 2 levels here because supersymmetry, there's no supersymmetry, so they're just independent. We take n to be the bigger field. So it's n to be the bigger number. So if we take n to be large, the simplest large N limit is you compare everything else to the biggest number. So I define lambda n to be n over kn. Lambda m is not m over km, but n over km in this limit. So you could do the other limit. So this is sort of a weakly coupled limit, and alpha you can take to be m over n, and you keep these fixed, and you try to do calculations. So in particular, let's calculate the anomalous dimensions of the single trace operators. Okay, and just the first order m over n calculations, these anomalous dimensions, these operators, if possible, all orders in these 2 coupling constants. Okay, and these are just how, so if you were to do it diagrammatically, these are the calculations. You have 2 colors and, okay, a diagram like this. Well, red is the bigger gauge field, blue is the smaller gauge field. Okay, so this is leading order in M over n, and this also contributes to vector models. This is subleading order in M over n, so it would not appear in a vector model calculation, but it appears to first order in M over n. This non-planar diagram is 1 over n, and it doesn't appear in the M over n expansion. So M over n expansion, you only keep planar diagrams, but you start with just the vector model diagrams, and you add more and more as you go to higher orders in M over n. Okay, and there's some more diagrams. So
you were computing what?
Well, I want to compute the anomalous dimensions of the same operators, J1 to J, the higher spin operators.
He's looking at the fermion.
If you're working with fermions, then psi has scale dimension 1. So psi bar psi is all you can write down. You can't, yeah, so just bivariant fermion. With bosons, it would be, you have to, I guess, think of the lambda 6 coupling.
Or you could do critical bosons.
Or you could do critical bosons, yeah. So at least in perturbation theory, I don't, of course, yeah, unless they get a finite results. So far, all I've done is I've considered these 2 cases where you set one of the coupling constants to 0 and the other all orders. I've not been able to do both of the all orders calculations. The first calculation is exactly the same as what I showed you earlier, only 1 over n becomes m over n. Okay, the second calculation is what I'll say next, and that's essentially a large flavor expansion. So in this case, it's just a large flavor expansion, so we can do the calculation without much difficulty. The anomalous dimension of the scalar operator looks like this, so it goes down and then goes up to a finite value. For the higher spin operators, we can calculate the anomalous dimensions. There, it never goes down, it always goes up. And the lambda dependence is a little different, but there's still log S behavior, and this is the result, which we just get from Feynman diagrams. So that's it. Okay, so congratulations and thanks.
I just wanted to mention, you talked about ADS4 cross a 7 mod ZK,
Right.
where ZK breaks supersymmetry, right? Did you talk about that?
Well, I don't have a dual of these theories. I just said that we know ABJ, I mean, we know that if you did ABJM at fixed K, we expect its dual to ADS4 cross.
You could consider some kind of supersymmetry breaking or bifold.
Of S7.
Yeah.
And see.
In fact, my former student Arvind Murugan looked at, there is this Horowitz-Argera-Palczynski instability for that case, kind of tunneling to nothing, and he showed that so those non-SUSY spaces can be non-perturbatively unstable.
Leading order and 1 by n, they just have the same thing.
Right.
Set.
Yeah, it's. I think in that case it is related to these triple traces at weak coupling, but at strong coupling or double traces, there are some double trace beta functions, but if you just go at strong coupling, there are these tunneling to nothing instabilities, kind of. And he found, actually, he posted his thesis a couple of months ago.
So the theory is not conformal at any point.
Well, naively it's conformal, but it has this catastrophic sort of instability. Yeah. Horowitz et al. Studied this first in ADS5 cross S5 mod ZK. There are these examples, freely acting examples, and they found this tunneling to nothing. And here there is a similar.
Is it a perturbative thing? Because an operator phi bar phi, psi bar psi, that
Yeah.
Right in the first part of your talk where you just talked about the anomalous dimensions, is there, you had the log S term, but you could do a systematic expansion.
Then it's just, I think, finite after that. There's no
only power law terms. Yes.
So this is the thing. So this is log S, and then you just get a rational function. No. So this just, if you expand this is log S plus constant or something. So there's just log S, and that's, and 1 over S space.
The next order, yeah.
We calculated 1 over n squared just in perturbation theory. And there we don't even get a log S actually for that. So beyond this. But that was just classical equations give you order 1 over k. So that's just 1 over k squared. Not the, at least to first, so lambda squared over n squared, there's also nothing more than log S. No log S squared.
Yeah, but maybe
at higher order in lambda, maybe, yeah.
Because there is the general large spin things from the bootstrap where you have general predictions for the form. Definitely in the bosonic case, there might be slight changes in the fermionic case, but in the bosonic case for which you said you have similar results.
Both boson, I think just bosonic case. I don't know if but at order lambda squared, we didn't find, over n squared, we didn't find log S. But
what I meant was whether there could be some meaningful comparison with the general form predicted by the bootstrap for these anomalous dimensions, in which the coefficients of the logs and so on are also related to the dimensions of the scalar operator, which you couldn't compute.
Yeah, we couldn't compute that.
But that maybe by comparison,
we could get what you expect.
Try to make a prediction or something for the scalar operator.
Right. That would be interesting.
Okay. And another quick question.
there's some sense in which all of these operators, these higher spin operators, including the scalar operator, are in one multiplet of the higher spin symmetry. I was wondering whether you could use that observation to get the scaling dimension of the scalar operator, sort of like Wigner-Eckhart theorem.
Perhaps it should be possible. I mean, it seems from perturbation theory that, for instance, it might look have a slightly different lambda dependence, but I'm not sure.
You said Giombi, and I think Giombi and maybe Sforza, some combination of these people, they tried to determine the leading order anomalous dimensions using broken higher spins.
No, this is that thing with them, yeah. But we just use the divergence.
Use just
the divergence.
But not the
we didn't really use the higher spin symmetry.
Right, but but wasn't there a separate paper which maybe I'm mistaken,
No.
used the higher spin?
As of now, we've not done the J0 anyway, as far as I know. But possibly it can be done using the higher spin symmetry. Yeah.
Shall we move on?
Okay.
Understand there are